Hi, my name is Diego Sanz Aguilar, and we are going to present experiment 7. First, I'm going to explain the theoretical concepts. First is the concept of electrostatics. That is the study of electromagnetic phenomena that occur when a charge is not moving. Next is the nature of electrical charges. If a charge experiences a force to the right, it is positive, and if a charge is going to the left, it is negative. Also, you can determine if a charge is positive if it has more protons than electrons, and if it is negative, has more electrons than protons. The point is that how bodies are electrically charged. There are three methods to electrically charge a body, and they are friction when they are rubs against each other and both objects get electrified because of the transfer of the charges. Another method is by conduction when a charged body has a contact with a neutral body. And the third one is, and the final method is by induction when an object is near to another object that is uncharged, and the first object induces an unlike charge near to the second object. The fourth point is the Coulomb's law, that is the electrical force between two charged objects is directly proportional to the product of the quantity of the charge on the objects and inversely proportional to the square of the distance between two objects, and this is the formula. And next, my partner Leonardo will present the first experiment.
Well, hello, my name is Leonardo Gonzalez Bustos, and I'm going to share with you how I did the experiment. Well, first we need this sweater, the balloon, and the wall. We can see that each one of them has its own charges, the protons and the electrons. And now, what happens if we rub the balloon against the sweater? We can see that all the electrons attached to the balloon, and this means that the sweater gave all his electrons to the balloon, and just as we saw like past, we have like balanced objects and charges, but now we can see that the sweater is only a positive one due to its loss of charges. Now, what happens if we put the balloon closer to the wall? We can see that it attaches due to the difference of charges, but the same charges repels. And this is a very known concept in physics. And this happens because the opposite charges seems to attract each other, but the same ones repels. Now, if we have a second balloon and we put half and half of the charges from the sweater on it, and we try to join the balloons, we can see that they repel due to they have the same electrons, and they have the same positive, the same sign, and this means that they're going to repel. And this happens due to electrostatic. And we can say that the sweater that we are going to suppose that is made of wool gave all his charges, and so now it's a positive charge. Now I'm going to give the word to my classmate Angela Ayala.
Thank you, Leonardo. My name is Carlos Ángel Ayala Alvarez, and I'm going to present the experiment too. Well, here we have the simulator, which gives us all the values already. We have the first charge that is -4 microcoulombs, and the second charge that is 8 microcoulombs. If we see these are opposite signs, so we can tell already that they attract to each other. Now the simulator is already giving us a force given between each other that is 319.557 newtons. Now we only want to make sure that simulator is right. So we can see already here that we have the data already given, the first charge, the second charge, the radius between each other, which is 4 centimeters, the force already that is given to us, and well, as Sansa said, that we already have a formula which is as K, that is 9 times 10 to the power of 9 coulombs. We have here the formula as well. Like I said, we just have to prove that the simulator is right. So we substitute. The force is this one, so we multiply and 9 times 10 to the power of 9 times the two forces and divided by the radius, the square radius. At the end, it's going to give us something like this. So we can tell that this is not equal. So if we pass to the document, give me a sec. So if we see, we already said that the forces are attractive to each other because there are opposite signs. The electrostatic force that we have when we made the procedures is minus 180 newtons, and we see that the simulator value is not the same. So that was everything for me. Now I'm going to pass the word to Victor Naum.
Hi, I am Victor Naum Vidales Juarez, and I'm going to explain to you the third experiment. Well, for the third experiment, it says that we need two charges. The first one with a value of 2 microcoulombs, and the second one with a value of 6 microcoulombs with a separation distance of 5 centimeters. Well, for the resolution by hand, we only need one formula, which is the electrostatic force formula, which says that the proportionality constant multiplied by the absolute value of both charges multiplied by themselves divided by the square of the distance between both charges. Now, by simply substituting every value, the respective values, we get the result of 43.2 newtons. Now, is it similar to the simulated value? Yes, they only differ by 0.06 newtons, but it's kind of the same. And what happens if one of the particles has an electric charge of 0? Well, then what happens is that everything else gets cancelled. There's no electrostatic force, and it just simply doesn't exist. And yeah, that was it.
We are going to say our team conclusions. Each one had their conclusion by the part that they did. Well, I did the theoretical part, and in conclusion I learned about the many theoretical concepts of the exercise 7 that are the concept of electrostatics, the nature of electrical charge, like how to know when I have a positive charge or a negative charge. I also learned how bodies are electrically charged, like the methods to charge electrically bodies, and the Coulomb's law and the formula. And next, my partner Leonardo will say his conclusion.
Well, I learned from this experiment that how even though we can see atoms and their charges are always there since everything is made of atoms, and how we can use it for charged things with a positive or a negative charge. And with simple experiments we can see how they interact with each other, and explaining how opposite charges attract and same ones repulse. And in this case, a simple experiment as driving a balloon to a sweater can change all the charges and their interactions and how they interact with the surroundings. And now with my partner, Angel Aguilar.
With this topic, I've learned that electricity fields are useful nowadays because much of the stuff we use uses electricity. And if we wouldn't know how to calculate electric fields, we would be electrocuting ourselves every time people try to build a house or a simple computer. Now with the simulators, I've made sure how the chargers work by being different signs. I proved that the charges in an electric field are very important because they can be repelled or attract to each other. Now I'm going to give the word to Victor Vidales.
Well, hi, I did the third experiment, and what stays with me after completing this practice exercise is that it doesn't matter how large a charge is, doesn't matter if it has 10 microcoulombs or 30 microcoulombs. If the other charge is equal to 0, then everything is going to be cancelled and it's going to be equal to 0. Why? Well, because in the formula that we use to calculate the electrostatic force, both values of the charges get multiplied by each other. So if one of them is 0, then everything else is going to be 0.
And that will be everything for all of us. Thank you very much.